Okay, so it's a great pleasure to have Riccardo Argurio from Brussels, and he'll talk about spontaneous non-invertible symmetry breaking. Please take it away.
Okay, thank you very much. First of all, I would like to thank the organizer for inviting me in this online seminar series, and I feel honored to be on the list, having seen the list of the previous speakers. Okay, so the title of the talk. So I see that I like the fact that it's called Symmetry Seminar. So the portion of introduction will be reduced according to the fact that I'm talking to experts. But my particular focus will be on spontaneous breaking of non-invertible symmetries, which is in some sense the common aspect of my recent papers that I listed here, and which I've done with the wonderful collaborators that are listed in this opening slide. Okay, so of course, as every speaker says, feel free to interrupt me, and all questions are welcome. Okay, so so this is the motivation slide that, as I just said, is probably not really necessary in front of this audience. But let me just say that my recent work has been in the context of this renewed interest in symmetries in QFT. And it's probably fair to say that the turning point in this renewed interest is in this paper by Nati and collaborators, now almost 10 years ago, where the main message is that symmetries are embodied by topological operators, and most of all, also all topological operators in a QFT must be interpreted as symmetry generators. So this understanding has led to realization of symmetries with respect to the textbook symmetries, let's say. In particular, symmetries acting on extended operators or higher form symmetries and non-invertible symmetries. So, as I said, my focus will be on spontaneous breaking of symmetries. And well, we all know, again, in front of this audience, I don't have to motivate how important it is to consider quantum field theories where the vacuum breaks spontaneously a symmetry of any sort, at least in some phase of the QFT that is being considered. And I would like, first of all, to underscore that we have to distinguish in this case between what happens for zero-form symmetries and for higher form symmetries. So in zero-form symmetries, first of all, the breaking of zero-form symmetries comes because of a condensate of some local operators, which has a dimension, a scaling dimension. And at least on spacetimes with a spacetime dimension larger than 2, the spontaneous breaking of a zero-form symmetry leads to the degeneracy of vacua. We'll see according to the symmetry whether the degeneracy is continuous or discrete. So this is obviously something well known from decades, but which, as I said, for textbook symmetries, is well known for invertible symmetry. So the question that I will address in this talk is what about non-invertible symmetries? So we'll focus essentially on non-invertible zero-form symmetries because I'm interested in vacuum degeneracies after spontaneous breaking of symmetry. So that's why I focus on zero-form symmetry. So non-invertible symmetries, again, a very brief reminder, are symmetries. So let's say that we say usually that the theory has a non-invertible symmetries if at least some elements in some symmetry defects act like projectors on some charged operator of the theory, meaning that then if they projected them out, we cannot undo the symmetry transformation. Okay, so in that sense, they are called non-invertible. And so I will, so these non-invertible symmetries have been, at least in a dimension, as I again emphasize that I would like to be in dimensions more than 2, space-time dimension more than 2. Actually, I will focus for the rest of the talk on 4-dimensional physics. And since we focus on broken symmetries, these non-invertible symmetries have been studied recently in higher dimensions, and let's say they appear in many forms in different contexts, but a rough classification is the same as the ordinary symmetries. So we have a non-invertible symmetries where the elements take values in a discrete set, or they can be in a countable, infinite but countable set, or they can be in a continuous set. Okay. So let me give examples of each. And these are also well known to the experts. So from the discrete set, these are the ones which have been studied perhaps in more depth. And these are actually the first examples of non-invertible symmetries in 4 dimensions in the papers listed here. And so these are finite orders, so in particular order 2, order 3. So this is duality, like the generalization to 4D of Carmens-Vanier, reality of order 3, and then generalizations of order n. So this is what I call discrete set. Then we have countable infinite set. In this case, the examples which have been put out also like a couple of years ago are actually the set where they take place is like the rationals, the periodic rationals, and this type of non-invertible symmetries appear in theories where there is some axial symmetry which is supposed to be anomalous. Let's say it's textbook anomalous, but then comes back in non-invertible fashion, but taking values in this countably infinite set. And then we have also continuous non-invertible symmetries which arise in for instance, the simplest example is which has been studied in many papers also recently, is the one of like O2 gauge theory. I will talk about all these examples, so I'm not going to get into many details now. But okay, so as I say here, I will go over examples of all these non-invertible symmetries and discuss the spontaneous breaking of each kind. Okay, so I will try to this. I'm just trying to. Okay, I can do it. Okay, sorry. I was trying to remove this bar. I don't know if it's seen for you, but I can see the title. But it's not.
We can see the title. No worries.
You can see the title, so I can. Okay, okay, good. Okay, so the first example is so this is basically from these papers, but let me review it because I think it's kind of a paradigmatic example that is important for the rest. So let us consider a theory which some standards might be like a very simple theory. So it's a super Yang-Mills, so it's Yang-Mills, n equal 1. And we will consider, let's say, gauge algebra SUN. But as we have been taught in the last years, we have to care about what is the global form of the gauge group. But let's, for the moment, okay, consider the gauge group to be SUN, so the global form SUN. So when the global form is SUN, and this theory is extremely well known. So it has an R symmetry, which in this case is, you can call it the axial symmetry of the gaugino. It's an R symmetry. It's a zero form symmetry, and which is a Z2N. And then, because the gauge group is SUN, it has also a one form symmetry, which is Zn, which acts on Wilson lines, which are the genuine lines in this global form, which is SUN. And then this has been observed, is that there is a mixed anomaly between these two discrete symmetries. And this mixed anomaly, we can consider it in many ways, but one way to show it is that under like an R-symmetry rotation, so this is like, let's say, the elementary, the smallest R-symmetry rotation in Z2N, then we see that in the presence of a background for the one-form symmetry, we generate this phase. But this is again the Pontryagin square of B. B takes values in Zn, it's an integer, but since we have a fermion, it's n equal 1, we are on a spin manifold, so this integral is even. And so eventually this phase is in Zn. Okay, so this is a very interesting observation that we can make if we turn on a background for the one function. Then let's assume that as it has been assumed in the last at least 30 or 40 years, that this theory confines in the IR. This means that the Wilson lines have area law, so that their expectation value is 0, so that the one-form symmetry is unbroken, no? Because the Wilson lines are the order parameter of the one-form symmetry. So confinement is equivalent to saying that the one-form symmetry is unbroken. But then this mixed anomaly implies that it is impossible for both the one-form symmetry and the R symmetry to be unbroken in the vacuum. Actually, the fact that the anomaly takes value in Zn tells us that the zero-form symmetry has to be broken to Z2. And then in turn, this means that the theory has to have n degenerate vacua. And breaking from Z2n to Z2. This is the usual thing when you break a vanilla zero-form discrete symmetry. So this is very good, very well, and it matches with what was known already for 40 years also, which is that this theory has a Witten index that tells us that they are in vacuum. Okay, so this is, as I say, a postdiction. But if we had not known about the Witten index, that would be a prediction. Okay, so, but this is again, so what are the properties of this vacuum? Well, they're all confining, so they're all equivalent, they are distinguished. So locally, let's say that we can, there is a gaugino condensate, which a bilinear gaugino condensate, which whose phase is rotated by the R symmetry transformation. So the gaugino condensate has a different phase. So the bilinear has values, takes values in Z, and so the phase changes in alpha. And another observation, so this is something that can also be observed and is related to the mixed anomaly, is that, or we can also go to n equal 2 and analyze the theory as breaking n equal 2 to n equal 1 from the Cyber-Witten description of this theory. But we can also see that the confinement in every vacuum can be linked to the condensation of a typically a dion. And the dion that condenses in every vacuum is different. And we'll be labeled so with a magnetic charge 1 and then an electric charge K. Okay. So now, okay, so this is well known from for SUN. Now the question is, what happens if we think that the global structure of the gauge group now is PSUN? So in other words, so I will take the global variant where the genuine lines of PSUN are the top lines. Okay, so this again, I assume that the audience is familiar with the fact that I can define the global variant of a gauge group by so the global variants of the gauge groups in 4D gauge theories are determined by what are what is the line or lines generating the mutually local lines of the theory. Okay, so in this case, I can assume here that the top line, so it's the line generated with the charge 0 electric charge and 1 electric magnetic charge. Okay, so this is the PSUN. And okay, so this is the definition of PSUN, but in particular, the way we can, let's say, the operation that we have to do to go from SUN to PSUN is essentially a very simple operation in some sense, which is gauging the one-form symmetry of SUN. Okay, so in other words, means that the background gauge field B that we turned on before for the one-form symmetry becomes a dynamical, though discrete gauge field for this one-form symmetry. So, okay, very good. So it seems like a simple operation to do, but given that we had this global anomaly here between the zero-form symmetry and one-form symmetry, now if this field B becomes a dynamical field, so we have to sum over the configurations of this field B, then this is no longer a 't Hooft anomaly, but becomes an ABJ-like anomaly. So again, if we go back to our textbook understanding of QFT, we would say, okay, then this mixed anomaly means is now an anomaly that is explicitly breaking the asymmetry group. And in particular, it's going to break it to Z2, which is the only part, subgroup of the asymmetry group, which trivializes this anomaly. Okay, so this is something that we can also see by saying that the periodicity of the theta angle in PSUN is actually 2 pi n instead of 2 pi as it is here. Okay, so that would be if I would say what are the, let's say, invertible symmetries of this PSUN theory, then the asymmetry is just Z2, the zero-form symmetry is just Z2, and the one-form symmetry is again Zn, but it's the magnetic one-form symmetry. But on the other hand, the low energy dynamics of this theory is basically the same, in the sense that waves of operators are still going to be the same as in the previous version. These are basically determined only by local aspects of the theory, so essentially by the gauge algebra. So we actually expect this theory to still have n vacua. And we also expect the wave of the Wilson loop, though now it's no longer a genuine state in the sense that it's not mutually local with respect to the 't Hooft loop. So in some sense, the Wilson loop is only defined if attached to a magnetic symmetry, an open magnetic symmetry effect. But still, we can, it has a meaning to compute its wave and say that it is zero. And so this n vacua, we can see what happens in them. But for instance, remember that the vacua were specified by a different line condensing in each vacuum. And so in particular, in one of these vacua, the 't Hooft line is condensing. And so we see that in one of these vacua, the one from symmetry, the magnetic one from symmetry of the PSUN theory is broken because the 't Hooft line, which is charged under it, has a wave. While in the others, the 't Hooft line, I mean, the other object condenses, so the 't Hooft line has a zero area law. And so the one from symmetry is unbroken. So the one from symmetry of the PSUN theory is broken in one vacuum and is unbroken in the other n-1 vacuum. Okay, so, and on the other hand, the Gugino condensate has a wave, again, because it has it also in the SUN theory. But in this case, the Gugino condensate is not charged under the Z2 symmetry, which was surviving. The non-anomalous invertible Z2 symmetry. So one might ask, why are there n-degenerate vacua in this theory? What dictates the fact that there are n-degenerate vacua, besides, of course, what we know about the Witten inverse? So the fact is that actually all the asymmetry defects of the SUN theory, they actually all survive in the PSUN theory, but now they become non-invertible. So in particular, so the elementary defects, so the one which implements the 2π/2n rotation is still there. It still acts, implements the same rotation, asymmetry rotation on the local operators, in particular the Gugino and the linear. But it acts non-invertible, so in particular it acts as a projector on the 't Hooft lines. And so, and this is because of this non-invertible action on the 't Hooft lines that these non-invertible symmetries allow for the degenerate vacua to have different physics, in particular confining or non-confining, with respect to the magnetic one from symmetry. Okay, so the whole point of this example was to emphasize that this is the recurring theme of all the examples that will follow, which is that the physics in vacua, which are related by non-invertible symmetries, so when non-invertible symmetries are broken, then the degenerate vacua will have, in general, different physics. By different physics, I mean confining or non-confining. So let's then discuss first a result which is similar in spirit to the previous one, but which happens in a non-supersymmetric theory. The interest is that in the previous case, we had essentially the degeneracy. Okay, I was saying emphatically what dictates the n vacua, but obviously supersymmetry is a big ingredient in that also. So let's forget about supersymmetry then and see an example where we can have similar arguments but without supersymmetry. So this is a paper that we did with Romain, a student of mine here. And so the idea is to have a gauge theory where there is a non-trivial one from symmetry, so something which is not the the usual super procedure, let's say. But in this case, so let's focus, we give several examples, but let's focus on the simplest, which is to have a SUN gauge group, or let's say gauge algebra for the moment. And we will consider as matter just a Dirac fermion in either the antisymmetric or the symmetric representation. So this means that the anality of the representation is 2. And so when n is even, this the anality tells us that a Z2 electric quantum symmetry is preserved. Okay, so this is the reason why we choose this kind of representations. And then, well, we can work out, so this matter content has an axial symmetry. That's basically why we choose only one Dirac fermion in this representation. But the axial symmetry, the classical axial symmetry, is broken by the BJ anomaly to this discrete group with +2 if it's in symmetric and -2 if it's in the antisymmetric. And again, there is a mixed anomaly between the one form symmetry and the zero form symmetry, which is very much similar to the previous one, essentially because the elementary, so the elementary transformation, the smallest axial symmetry transformation, basically implements a shift of theta by 2 pi. And so this is basically the anomaly in the space of couplings of SUN. But in this case, so this is essentially the same expression as we had before, but thinking as B as a field, as a connection, gauge field for Zn. So this takes values in Zn. But now, if we restrict the one form symmetry because of the matter field to Z2, which since n is even is a subgroup of Zn, then basically turns out that it's basically it amounts to write it in this way. These are the only elements of the original B which survive as background gauge field of the Z2. And so then we just plug in the formula, and this is basically the mixed anomaly which remains. Now remember that P here, the Pontryagin square, is odd, sorry, is even, because again we have fermions. So let's say that the 2 goes away with this, and n is even. So then we see that, okay, n is even, but then it can be either a multiple of 4 or a multiple of 4 plus 2. But if n is a multiple of 4, then we see that this phase is always 1. So basically, there is no anomaly when n is a multiple of 4. However, when n is a multiple of 4 plus 2, then the anomaly takes value in Z2. And in particular, the phase is -1 when K, which is the amount of axial symmetry transformation that we do, is odd. So, very good. So in both cases, so in particular in the case when n is 4p, this mixed anomaly is not enough to predict the exact number of vacua. But for sure, we know that since the anomaly is in Z2, in this case, when n is 4p plus 2, then there must be an even number of vacua. This is something that we can predict with this argument based on the mixed anomaly. Now, in this theory, we have a Dirac fermion, so we can write a bilinear condensate for this fermionic bilinear for this fermion. In particular, this fermionic bilinear can have a bev. There is actually no obstruction for this. And if it has a wave, then it's easy to see that the axial symmetry is broken to Z2 again. And this means that there must be n plus or minus 2 degenerate vacuum, which again is an even number, if is even, which is the assumption. So let's work out the simplest example, which contains already everything I want to say, which is SU6, and with a direct fermion in the antisymmetric. So this has 4 vacua. So it's an even number, but it's more than 2. And they are distinguished by the phase of the fermionic bilinear condensate. Again, we assume that W, so the Wilson line has an area law, so that the one from symmetry is unbroken. And so then we can also ask, so we said that we have these 4 vacua, they differ by the bilinear condensate, but also we can say, okay, well, they confine, but what is the line that condenses? And so we can say, okay, if let's say that if the top line condenses in this vacuum, then here there will be the dionic line. But then again, this should be the top line, and then again the dionic line. So essentially, we can distinguish only between 2 non-genuine lines in this theory, and so the vacua come in pairs. Okay, so now let's consider in this theory, instead of SU6 global form, we go to a global form which is SU6 over Z2. So this theory now, basically, so we're gauging here the electric one from symmetry, and okay, so by the process of gauging, we obtain a magnetic one from symmetry, and again, this anomaly that was a global anomaly here becomes a gauge anomaly. I mean, an anomaly involving a dynamical gauge field, so that we see that the axial symmetry is broken to half of it essentially, which in this case would be from Z4 to, sorry, so from Z8 to Z4. Okay, so the fermionic bilinear is still there, it breaks Z4 to Z2, but again, we have to explain here why there are 4 vacua instead of 2. So this breaking from Z4 to Z2 would only tell us that there are 2 vacua, but we know that there are 4 vacua from the previous discussion of SU6, global form SU6. And so essentially we want to know why the 2 pairs of vacua are degenerate. And the fact is that the generators of the original Z8 are still there, all, but some of them, essentially the Z8, the elementary Z8 generator, now becomes non-invertible. So in practice, so this is very similar to the SUN case that I discussed, the Super-Mills case. But essentially, in this case, is actually very simple to write. So the non-invertible defect M is built out of the, let's say, the invertible defect, and it has to be addressed by this 3-dimensional TFT, which is one of the minimal TFTs, which in this case it happens to be coincident with U1 Chern-Simons at level 2. And this is so this TFT is coupled to the the dynamical gauge field gauging the one-form electric symmetry. Okay. And again, this vacua here, now they are going to be different in this global form because the 't Hooft line is the genuine line of this theory, SU6 over Z2, and in two of the four vacua, the 't Hooft line has a wave, so the Z2 magnetic symmetry is broken, while in the other is still unbroken. And these non-invertible defects are able to relate this vacua with different physics because they act as projector precisely on this 't Hooft line. And this can be seen maybe in the simplest way by seeing that the fusion of two of these defects gives us the, let's say this is the defect, so it's the square of this, so it's just the Z4 generator, but times this, what this is now known as a condensation effect, which is precisely some of the lines of the one-form symbol. Okay. Which acts as a projector. Okay, so now I would like to talk about still about another kind of discrete non-invertible symmetries, which are the ones related to duality and triality defects. And so these are similar in spirit to the, let's say, the most celebrated non-invertible symmetry, which is the Kramers-Ranier duality in 2D. And so these defects arise in theories that have parameter space with self-dual points. So again, this goes back to the first papers that discussed non-invertible symmetries in 4 dimensions. And the idea is to start with n equal 4 super means now with gauge group SUN. And at some specific points of the conformal manifold, this theory, one can define non-invertible symmetries. So these are the points, the specific points at tau equal I, where one can define duality defects, and tau, which is a third root of unity, where one can define triality defects. These are related to the fact that doing like the S duality, let's say, and to stick to the duality defect, changes the global structure of SUN, but then can be changed back by gauging the one-form symmetry. That makes this gauging makes the symmetry non-invertible. However, n equal 4 super Mills is a very interesting theory, as we all know, but the zero-form symmetries in this conformal theory are unbroken. And as I said, I want to focus on spontaneous breaking. So a way to generate more interesting, or let's say less conformal dynamics from such a theory is to turn on masses for the joints that if we formulate n equal 4 super Mills as n equal 1, then there are 3 chiral superfields in the joint representation. We can turn on a mass for all of 3 of them. Okay, so this is a well-known thing that has been done in the 90s. And so this is what we set out to do with the collaborators listed here. And so this theory is called n equal 1 star, has been also studied holographically in very interesting papers. But we will focus here on the fact that this theory has a number of vacua, an interesting structure of vacua. And in particular, we're going to focus on the vacua which are completely gapped. So this theory has also vacua which have a Coulomb behavior, but we are going to focus on the vacua which are all gapped. And for SUN gauge algebra, this number of gapped vacua is given by essentially by the sum of the divisors of N. This is interesting, okay? But it's even more interesting because when one realizes that, okay, we start with the SUN gauge algebra, then we want to discuss the global variance of the gauge group. And then for SUN, again, as I just explained, we can discuss the global variance by listing how many lattices of mutually local lines one can describe. And it turns out that the number of variants is given exactly by the same number, the sum of the divisors of A. Okay, so that's a very interesting fact already. And let's start with the SUN global variant, which has a one from symmetry, which is Zn. As we already said, it's the same again because all fermions are in the adjoint. All matter fields are in the adjoint. So then we said that there is a number of gapped vacuum, and in every gapped vacuum we can essentially characterize the vacuum also by how this one from symmetry is realized. So in particular, if it's broken, partially broken, and according to how it is broken, it is going to be realized by a TFT, which can be like a trivial TFT, like a symmetry protected topological phase, or it could be also, if in the case, for instance, that the Zn is completely broken, then it will be like a Zn gauge theory in that vacuum. So in all generality, we can consider all the intermediate cases, and roughly we can write the TFT in a specific vacuum would be specified by an SPT phase for the unbroken part of the one from symmetry, and then a gauge, a discrete gauge theory for the broken part. Turns out that we can have the catalog of all these different TFTs for Zn one from symmetry. And it turns out again that the number of different TFTs that one can write is exactly the number of global variants, which is the same as the number of gapped vacua in this n=1 star theory. This is again a very interesting fact, and we can actually show that every vacuum is specified by what line condenses, and every line defines a global variant, and every line essentially determines what is also the TFT associated with the vacuum. So there is a one-to-one. So not only all the numbers match, but also there is a one-to-one-to-one correspondence between every global variant, every TFT, every line associated to a global variant, every TFT, and every gapped vacuum of n=1 star. Okay, so now what about this general fact about n=1 star? Now, what about the non-invertible symmetries in this business? Okay, so the dualities and trialities of n=4, the question is whether they survive in n=1 star. And the fact is that, in principle, turning on the mass deformation, the only thing one has to make sure is that this mass deformation does not break the symmetries. And the only way it breaks the symmetries is that the dualities and trialities actually act on the supercharges by a small phase rotation. It was explained by Kapustin and Witten. And the only thing that we need to do is to essentially implement an R symmetry which compensates this rotation. And once we do that, then the dualities and trialities persist as the symmetries of n equal 1 star. This means that these non-invertible symmetries are preserved along all the RG flow, because now this n equal 1 star theory is not a conformal theory, so it has a non-trivial RG flow. Of course, it ends up in a gapped vacuum. And so, but the symmetries, if we start from the RG flow from a self-dual point, then the dualities and trialities are going to be preserved around it. Then at the end of the RG flow, we are in a gapped vacuum, and typically these symmetries, these dualities or triality symmetries, are going to be spontaneously broken. So why do we expect them to be spontaneously broken? Well, the fact is that these symmetries, in general, they transform the line, they act on the lines, dualities and trialities. And since the gapped vacuum are associated to a condensing line, then since the duality and triality typically acts on this line, then they will break the symmetry. They will map one vacuum to a different vacuum. So then we expect the vacua to assemble in doublets of duality and triplets of triality, or singlets, of course. This is also possible. So for SU2, for instance, we have 3 vacua, 2 plus 1. So we have the Higgs vacuum where the Wilson line here. So this is notation where it says that the Wilson line has electric charge 1 and magnetic charge 0, condenses. Then we have the 2 confining vacua where the monopole, so the Toft line or the ionic line condenses. Here they are non-genuine in the global variant SU2, so here, hence this U here. So these are the TQFTs, which are only 3 in this case, that can be assigned to this vacua. So here we have Z2 because the one from electric symmetry is broken. Then we see that S duality maps these two, the Wilson line and the Toft line, while it leaves the diagonal line invariant. So we see that this vacuum here is a singlet of duality, while these two are a doublet. While under triality, the 3 vacua are a triplet, expectedly. So again, we see that this doublet and this triplet mix vacua with different physics. One is non-confining, while the others are confining. If we want to go to a fancier example, so this might have looked too simple. So this is SU4, which is a nice example in itself, has many features. But in particular, again, so this is global form SU4 here. We have 7 vacua, different kind. And so we see that in this case, again, we have like 3 doublets of duality and a singlet, 2 triplets of triality and a singlet. It turns out that this vacuum here, which is when there is some partial confinement, is a singlet of both. But the others here, again, we have, like, for instance, here, a doublet which mixes confining and non-confining. But here, for instance, partial confining to confining. But so, okay, and then we can consider. So this is okay for the global form SU4. Then we can consider the global form, which is SU4 over Z2. So this is we could also call it SO6 plus if we want. Then it's the same vacua again. The only thing that changes is now the genuine lines are these 2. Now we see that, okay, basically we chose as genuine line the line that condenses in the vacuum, which is a singlet of both duality and triality. So then you see that all the other vacua have the same behavior. Here, been maybe a bit too quick, so that there can be some SPT of the unbroken group here that decorate this Z2, but the physics is the same in all these vacuum. Only one Z2 is confined and the other is fixed. And so we see that duality and triality mix these vacua, which have the same physics. And indeed, it turns out that in this global variant, duality and triality are invertible. Okay, so it's really like now we start to see really a pattern where non-invertible symmetries, spontaneously broken non-invertible symmetries are going to map backward with different physics. Okay, so let me, so there is an additional curiosity about these models, n equal 1 star, which are in this work, again, late 90s, by mapping to integrable models and so on. In any case, we have a formula for the superpotential as a function of tau in each one of these vacua. Okay, so this is the notation we had before, and this is the expression in terms of Eisenstein series. And so this is a check in the sense that we can write, so essentially the observable, so like the Gugino bilinear, let's say, or like local observable that can be defined, is proportional to this superpotential. And so we can see at the specific points that we considered before, duality or triality, I mean, the points that start with at the dual point of duality or triality, we can see what are the relation between the superpotential of these waves in each vacuum. And indeed, we see that so this is for SU2, we see that the two vacua which were in a doublet are indeed related by phase, which is a -1 sign here, while the singlet, then the baby is 0. And while in the triplet, so the triality self-trial point, let's say, the waves of this local operator arrange along like the rules of unity. In SU4, we see that actually there is a vacuum which is both duality and triality invariant. Then is a singlet of both. And then we see that the only option is that the superpotential is 0 for both. So it has to be 0 at 2 points here. And then we can see actually straightforwardly from this expression that the superpotential is 0 for all values of tau. This is a funny remark. Very good for n equal 1 star. So, okay, very good. So, of course, again, I'm not getting any questions, so I hope it's because I'm too clear and not because I'm too unclear. But feel free, of course, to ask. So I'm moving on now very briefly. So, okay, I see that I'm a bit late, but I don't have much to say about these rational symmetries because they appear in models which are already like involve an axion, which is supposed to be already a goldstone for a broken U1, at least at the classical level. Then the Abijay anomaly would tell us that, well, the U1 symmetry is actually not a U1 symmetry, so it's a ZK. So then that would allow for a periodic potential for the axion that gives a mass. But actually, the non-invertible symmetry restores like a dense subset in U1. And so this basically preserves the masslessness of the axions. But I don't have much to say about this. So that these models could be considered as models where this Q over Z symmetry spontaneously broken. But let me go to this this last kind of non-invertible symmetries, which has received a relatively smaller attention, which, okay, so let me define it. It's very straightforward. So let's now simplify things, and let's go back to the to simpler models. So let's take the Goldstone model of the 60s. So this is just a complex scalar. Let's stick to 4 dimensions. And we all know that this theory, when the mass square is negative, has a vacuum manifold, which is a circle. Circle is isomorphic to U1. But what is less often discussed in this model is that this Lagrangian has another zero-form symmetry, which is discrete and which is charge conjugation. Okay, so good. But so the modes, the massless modes in the broken vacuum are Goldstone bosons, and the question is, what happens if we decide to gauge this discrete symmetry? So let's consider at low energies the same model, which now is the model for the shift symmetric Goldstone boson. So this is the phase of the previous field. So it has a shift symmetry, and the charge conjugation will act by reflection on this compact scalar. So the question is, what is so now we want to gauge this charge conjugation, so this reflection symmetry, Z2 symmetry, and the question is, what happens to the vacuum manifold, which was a circle? Okay, so again, let's emphasize that we are in more than 2 dimensions. So we have a vacuum manifold, and obviously, what I mean, it's kind of intuitive to say that the vacuum manifold is going to be an orbifold of the circle, S1 over Z2, no? Where the reflection of the circle. Okay, so this is so what's the big deal with this vacuum manifold? Well, it is a sort of a big deal with respect to the usual case, because now we are in presence of a vacuum manifold which has 2 singularities. So there are in particular 2 orbifold singularities, phi equals 0 and phi equals pi. And so in particular, we would like to say, okay, if we say that there are the Goldstone bosons take us around this vacuum manifold, then what happens when do the Goldstone boson have specific properties when they reach these singular points? Okay, so first of all, so let's discuss, okay, I have just 2 minutes, but let me be brief. So the idea is that we just gauge, so how did we gauge the charge conjugation or the reflection symmetry? Well, we just introduce a one-form, so it is a zero-form symmetry, as I emphasized, so there is a one-form gauge field, which can be a discrete Z2 gauge field. But this Z2 gauge field has so in the theory where the reflection symmetry is gauged, then there will be line operators defined by this gauge field, which are going to be Z2. So in particular, they implement a quantum symmetry, which in 4D is a 2-form symmetry. And they will have so they will measure the charge of objects, which we can call the reflection vortices. Vortice is when you go around, then phi takes a minus sign. But so these line operators in particular will tell us that of all the local operators of the ungauged theory, let's say half of them will survive as a genuine local operator. So these are the gauge invariant ones. And then the other linear combination, we can write it in this way. This is going to be gauge invariant only if we attach to them a semi-infinite line of this Z2 gauge field. And so these are called non-genuine operators. But we can also, in other words, we can define them alternatively by we can actually define this this field phi. We can define like a non-genuine or twisted field by attaching. So this field is local, but it's non-invariant under the Z2 or the gauge Z2 reflection symmetry. We can attach to it a semi-infinite line and define a non-genuine or twisted field, from which we can define both the genuine or the non-genuine. Okay, so let me, I see that my time is up, so I don't want to be too long, but let me, okay, so what I want to say here is that this is the approach that has been used also defining a similar story for Maxwell. But so the symmetry defect, so this would be like the naive symmetry defects would look like this in the gauge theory. But the problem with these symmetry defects, they have both, let's say if we expand it, they have both the powers of this charge, which is non-genuine. And so these operators are neither genuine or non-genuine. But so if we take like a symmetric combination, then we will have genuine symmetry defects. So these do not have any line attached to them. But if we act with these operators on the genuine local operators like this, then we see that the outcome is something that for some values of alpha and n can be zero. So these again are projectors. But in this case, so in this theory, the non-invertible defects act on the local operators already in a non-invertible fashion. Remember that in the previous examples, the non-invertible defects would act invertibly on the local operators, but we would see that they are non-invertible because they would project out lines. But in this case, it's really on the object on which they are supposed to act, let's say, that we already see that they are non-invertible. Moreover, we can see that they have also non-invertible fusion, but that's kind of no. Let me, okay, say, get to the end of this example by saying that we can define similarly as before. So like if this theta, this vacua, these are the vacua of the, let's say, ungauged theory, then we will have the untwisted vacua will be linear combination when theta is different than 0 pi, but actually the vacua 0 pi are invariant by themselves. Then we can also define the twisted vacua, so the vacua which are odd on the Z2. And then the fact is that we can build the Hilbert space by acting with phi prime, so the twisted field on this vacua. But so on the physical Hilbert space, so the space of, let's say, genuine states, is obtained only for states where there is, let's say, an even number of twists. So we can act with a, so in particular, we can add with a twisted field on the twisted states or two twisted fields on the untwisted vacuum. But so in particular, we see that for theta between 0 and pi, we can have single particle states because we can act with a twisted field, with only once with a twisted field on the twisted vacuum. However, on the singular points, which don't have like a twisted version, we have no other option than acting with twice with the phi prime, with the twisted field. So basically, then the bottom line here is that only, let's say that the Hilbert spaces at the singular points are different from the Hilbert spaces at non-singular points because of the fact that there are only pairs of non-Wilson bosons. Okay, so again we see so the non-invertible symmetry is broken in all of this vacuum manifold, but still the physics at different points of the vacuum manifold is different, even though it is related by non-invertible symmetries, also in this continuous case. Okay, so sorry for taking 5 more minutes. The outlook is, well, I don't have much to say. The outlook is just to say that I think it's a very interesting subject in general, and I try to motivate like say, an angle of approach of non-invertible symmetry, which is the one of spontaneous breaking in theories where there is, let's say, a non-trivial energy flow. And okay, I think there are a lot of open questions. Let me mention only one, which is okay, what happens at finite temperature in all these models? No? How are non-invertible symmetries restored or not at when we heat them? Okay, so that's I think good enough. So thank you very much.
Thanks very much for this really clear talk. Other questions? Have you thought about formulating all of this sort of more from a SIM-TFT perspective?
Well, the SIM-TFT is
So you basically put gap boundary conditions on both sides for the symmetry and for the theory, because the gap phase basically is modeled in this way.
You mean for the discrete? I mean,
yeah, for the discrete
okay,
case. Yeah, sorry. Mm-hmm.
In the discrete case, yeah, I think I would say that the symmetry TFT is just going to tell you. Okay, so the symmetry TFT is going to tell you what are the symmetries along the RG flow, right? So the choice of the global structure of the gauge loop and the UV, and additional symmetries like duality and triality. So the theory is going, the symmetry TFT is going to be more involved, but I'm not sure that the symmetry TFT can tell you the outcome of the RG flow, right?
I'll tell you about the generalized charges and the order parameters for this particular vacuum.
Yeah,
so,
this for sure.
Yeah.
Well, it will tell you in general, I think, but not going to tell you which objects are going to have a bear in which vacuum. No,
I mean,
I don't think that the
1+1
symmetry
DS.
is going to distinguish. Sorry?
In 1+1 DS, for sure.
It's going to tell you in which vacuum you end up.
I mean, it'll tell you which kind of order parameters you have in a given vacuum, what type of vacuum you will have. So that's the type of, you could ask this question. Generally, you have some particular symmetry in a 4-dimensional quantum field theory. And now you ask what kind of gap phases do you have, what order parameters do they have when you have also non-invertible symmetries that are.
Sure. This I agree. I'm just saying that I don't think that the symmetry TFT is going to tell you, let's say, take n=1 super means SUN or PSUN as you prefer. The symmetry TFT is not going to tell you in which of the n vacuum you are going to end up.
No. It'll tell you the option.
I agree that it's going to tell you that how to distinguish between the vacuums, let's say. This I agree, yes.
I think there was another question, maybe Nadi, you had your hand up.
Well, I think I figured it out, but that's why I lowered the hand. But if I'm pressed, I'll ask it. When I look at your set of examples,
yes,
in which of them is the local physics the same, but only the global considerations are different? Like when in the example with SUN at the beginning, although the spectrum of globals, etc., is exactly the same, it's only the lines are different.
I would say so, yes.
And there you understand. Okay, so that's one. The question. So question one: is this true in all your models, or I couldn't do in real time the analysis of the last model? And the second question is: in which of your examples the non-invertible symmetry started its life as an invertible symmetry, which became non-invertible only after gauging, and therefore you could have obtained most of these results without ever mentioning the non-invertible symmetry?
Yeah.
The two questions are actually closely
No,
related.
sure. I think that, no, okay, yes. All the examples, the non-invertible symmetries arise because of the gauging of the symmetry. So indeed, like for instance, in the n=1 example, the super-Mills example, as I tried not to hide too much. I mean, we know the results from the written index and so on. So I think, yeah, I think that the local. So to go back to your first question, I think the local physics is the same, at least in the gauge tier examples, is I would say is the same. And it's really when you start talking about the lines that you would distinguish. So in other words, I know because I mean, sometimes even discussing with colleagues which are not working precisely in this field, it's difficult to say, okay, well, the Wilson line is non-genuine, it has a zero wave, but we still call this vacuum non-confining, you know? So then sometimes people say, no, but what do you mean? It is confined. So it's true that when we say that PSUN does not confine in a vacuum, well, we have to specify what we mean. So in that sense,
no, that you don't have to convince me of that. I think I
no, I know. I'm just
but the
saying
question is
for the wider audience.
When you had dynamical results like vacuum degeneracy and all that, which of them? There are two questions. Which of the different vacua the same locally but different globally, or are they also locally different? So that's question number one. And question number two, if the questions was discussed, say, 10 years ago, no higher form symmetry, no non-invertible symmetry, nothing. Would the same vacuum degeneracy, would it be derived or not? So the question is not whether we define it one way or another, but in the end of the day, we have a result. Can this result be obtained without the non-invertible symmetry or not?
Well, okay, so if you really push me, yes, obviously, I think I would have loved to present a result that cannot be, that the only way to prove it is by non-invertible symmetries, but that's not the case. As I said, all I managed to show today is post-diction in some sense. Also in this non-supersymmetric example, the number of vacua was already known from other arguments. But in the non-supersymmetric case, maybe you can say that the non-invertible symmetry is a further hint. So I don't know if you were mentioning when you said the last example, this obviously is on a different footing, no? This the Goldstone, the continuous example. Was that you were referring to that?
Yeah, that's the one I couldn't do in my head. Everything else I could do in my head. No,
that's it's a simpler in some sense example. There is no confinement or thing, but in that sense, in some sense you would like to say, okay, it is different, no, because the Hilbert space structure is different in the two vacua. But on the other hand, it's a kind of a formal difference, no? Because we are still talking about massless particles. So I mean, counting massless particles is not. I mean, if you start saying, you would have to talk about resolution, right? And then it doesn't make much sense. But that's why I think a further line of inquiry, which was related to this finite temperature, would be to work out whether this model would somehow manifest the non-invertibility when like let's say something like a non-invertible superfluid or something. But I don't know. This is like something we're thinking about, but haven't figured it out yet. I don't know if I answered all your questions.
Yeah, you did. Thank you.
Okay, thanks. Okay.
Okay, any other questions? If not, let's thank Riccardo again. I'll stop the recording.